So it's my great pleasure to introduce Kimbo. So Kimbo is a good friend and also an analyst and member of technical staff at SemiAnalysis. He conducts GPU performance benchmarking and writes technical deep dives on the AI hardware architecture. His work on the NVIDIA Tensor Core evolution and AMD versus NVIDIA inference benchmarks has become widely referenced in the industry. Like for real, people are relying on a lot of the stuff that Kimbo's putting out there. So it's quite amazing. And he helped build Inference Max. So this is an open source GPU benchmarking system used as an industry standard to compare different hardware. He holds an MS in computer science from UC Riverside and a BS from the National Tsinghua University in Taiwan. So please help me welcome Kimbo, and take it away.
Thank you, Mohammed, for the introduction, and thank you for inviting me to this class. Today I'm going to talk about the evolution of the NVIDIA Tensor Core architecture. So we also always hear there's a CUDA moat, and in my opinion, if CUDA is a moat, then Tensor Core is a dragon. So the goal is to talk about the Tensor Core architecture and how it evolved, and the principles behind that, and the trends that we see. First of all, why should you care about the evolution of tensor cores? And my argument is tensor cores are mysterious and important. We all know that NVIDIA GPUs have driven the major innovations in AI, starting from AlexNet with 2 GPUs doing pipeline parallel, and all the way to recently with all the crazy NVL72 GPU racks. But the issue with tensor cores is that tensor cores the architecture is becoming more and more complex, and it's difficult for ML practitioners to keep up with the design, the programming model, and the architecture details. But at the same time, tensor core is very important because it's critical to use tensor cores to achieve good performance. As we see in the graph on the right, the GPU dense throughput has skyrocketed for tensor cores with lower and lower precision. But if you see for the FP32, which is the normal CUDA cores, it's barely increased throughout the years. And the graph on the left shows that increasingly the higher percentage of a GPU, the total percentage of the compute throughput are from tensor cores. And we can see in the latest B200, it's like less than 10% are actually the CUDA core compute throughput. That's why I think it's very important to understand tensor cores. And in this talk, I'm going to talk about roughly in high-level overview of how tensor cores perform matrix multiplication from a programming model perspective, and then also 3 principles, 3 trends and the principles behind the evolution of the architecture. And so they are why tensor core size is increasing, the programming model is becoming single occupancy and how it's related to strong scaling. And finally, the trend of asynchronous execution and its relation to Amdahl's law. So first, how do tensor cores perform matrix multiplication? So before we start, just to make sure that everyone is have the rough background knowledge of CUDA programming model, here are some terms that we will use throughout the talk. Very roughly speaking, the programming model is SIMT, where the programmer thinks and codes in the perspective of a single thread, and then relies on the hardware to parallelize and run in a lot of execution units. On the left column are the execution units of different within a hierarchy. And on the right column, there are the corresponding memory pools that the execution units can access. So for example, a thread can has a unique set of register file to access. A CTA, or also called a thread block, can access a set of shared memory. And same goes for a grid to a global memory. So first of all, this is the overall workflow, the data flow of a matrix multiplication for the first three generations of GPUs that have tensor cores. So they start from Volta, and then Turing, and then Ampere. They all look roughly like this. And so the steps are, first, you load the operands, the input matrices, from the global memory to the shared memory. The second step, you load the shared memory into the register file, and then the tensor cores read the input from the register files, and then performs matrix multiplication, and then write back to a register file. Finally, in a typical matrix multiplication workflow, you would have an epilogue operation, which is typically element-wise operations such as activation functions or biases, something like that. So in terms of the programming model, it is a collective operation, meaning that it takes a group of threads working in synchrony to perform an MMA operation. MMA is the name of the instruction that Tensor Core executes. MMA stands for matrix multiply and accumulate. And then this is also the name of a PTX instruction for the Tensor Core. So here we mostly talk about PTX, which is the level of abstraction of the instruction that is most portable across NVIDIA GPU generations. So the major differences between Volta and Ampere, Turing is kind of like in between, closer to Volta. So I grouped them together. And so the major differences between Volta and Ampere are Volta uses 8 threads to collectively launch an MMA operation. And then while Ampere uses a warp of 32 threads to perform an MMA. The second major difference is that Ampere uses a different kind of instruction to load data from global memory to shared memory. It's called LDG-SDS. And the major feature is, a major difference of this instruction is that it can asynchronously load data from global memory to shared memory. We will talk about the why asynchrony is important later. Should we answer any questions before we move forward, or should we just do it in the end? And maybe let's do it in the end then. Should be okay. Okay. So the next generation is called Hopper. Hopper uses a version of MMA instruction called WGMMA. WG stands for warp group. So instead of using one warp to launch one MMA instruction, it uses a warp group, which is 4 warps to launch an MMA operation. So in total, it needs 128 threads. The other major difference of this MMA operation is that of this instruction is that it's asynchronous. Again, starting from the data loading, now the MMA operation is also asynchronous. The second major feature of Hopper is that it has a dedicated hardware unit called Tensor Memory Accelerator, TMA. This hardware is dedicated to do memory loading from global memory to shared memory. It handles address generation. It also has out of bounds detection and a couple interesting useful features that makes it easier to program. And the most notable difference of this TMA unit is that it has single thread semantics, meaning that you only need one thread to launch the whole launch an instruction and execute on the whole unit. This is a very big departure from the typical CUDA programming model, where we talked about we used for a CUDA programming model we code the flow of one single thread, and we expect the GPU to launch a lot of threads to get high performance. But right now, it's designed to use only one thread. Another detail of the WGMMA is that right now, it actually reads data from SMEM rather than register file, which is also like a slight change compared to Volta and Ampere. Okay. So the most recent generation, Blackwell, the MMA instruction is called typically called UMMA. And then on Blackwell, Tensor Core has a family of different kinds of instructions. They're also the family, they also call it TC Gen 05. So yeah, TC Gen 05 MMA, UMMA, like TMA, has single thread semantics. So again, it's a departure from the CUDA programming model, where you only need one single thread to launch a full MMA instruction. Unlike Hopper, you need 128 threads. Unlike Ampere, you need 32. Unlike Volta, you need 8. The other major feature of UMMA is that you can actually launch one MMA that executes on two SMs. So instead of launching one CTA or one thread to execute it on one SM, you now can actually use two SMs to collaboratively run a very big, a relatively bigger matrix multiplication that uses two SMs, and the hardware will collaborate underneath in a specific way. The second feature is that it's called tensor memory, which is a different thing from tensor memory accelerator. Tensor memory is actually a dedicated memory unit for tensor cores that is dedicated for tensor cores to use as a register file. So it replaces a register file as the location that you store your operands, specifically the input matrix A and the output matrix D. This TMEM tensor memory has a very unique architecture. It has a very restricted memory access pattern. Specifically, you need 4 warps to access the whole tensor memory, and every warp can only access one specific region. The major benefit of restricting the memory access pattern is for power efficiency. By reducing the number of access patterns, you could design less memory access ports. And from the hardware design perspective, you could save a lot of power. And the other major thing is that tensor memory does not restrict, unlike register file, which is assigned to a specific thread. and no other thread can access the unique set of register files. GMEM is designed so that all warps can, different warps can access the same region, as long as they're in like the specific order of 4 warps. And this feature comes very handy when it comes to advanced programming patterns like warp specialization and like the ping pong kernel related. It makes programming the ergonomics better. Okay, so yeah, that is like a very quick overview of what's happening in the MMA and the Tensor Core architecture and programming model. And next, we're going to talk about the 3 trends and the 3 principles behind the evolution of Tensor Core. So first, we see that Tensor Core size is increasing. So more concretely, Tensor Core can process larger and larger matrix multiplications. And the motivation is quite straightforward because matrix multiplication has a linear time arithmetic intensity. So if we break it down, because matrix multiplication is cubic in terms of computation, but quadratic in terms of memory load. So that means that the larger it scales along the arithmetic intensity, and that when we want to scale performance, it's a very easy thing to reach for. So because we need to run larger matrix multiplications, we need more threads to gather a bigger pool of register files to launch MMAs. So that's why we see, starting from Volta, you use 8 threads, and then 32 in Ampere, and then 128 in Hopper. The other benefit of having a larger tile of matrix multiplication is that given the same matrix multiplication size, using a larger tile in the block matrix multiplication algorithm actually increases data reuse. So people can refer to tiled matrix multiplication and derive, you can see that it actually saves more. So the principle behind why we care about increasing the size, increasing the matrix size, and increasing the data reuse is because in terms of physics in our world, it turns out computation is a lot cheaper than data movement. So data movement is jokingly in high performance computing considered as a sin, meaning that the fewer data movements you can do, the better. Okay, so the second observation and the principle is that the programming model is getting closer to single occupancy, low occupancy to single occupancy, and it's related to strong scaling. So for people who have learned how to program to do CUDA programming, I think everyone probably learned definitely learned some of that for the non-deep learning workloads. And the major idea behind non-deep learning workload is actually oversubscription, meaning that we would want to create and split up a problem into a lot of working units, ideally more than the number of workers we have, and use parallelism through assigning every worker multiple working units, and they can context switch between the working units that they're assigned in order to achieve better performance. A concrete example would be if we split a work into multiple working units, and one worker has one working unit waiting for data loading, it can switch to another working unit to do computation to hide the latency and improve performance. Under this paradigm, we would try to achieve high number of active workers. In CUDA programming's case, it'll be high number of active warps. And the terminology we call this is called high occupancy. So high occupancy is the key to non-deep learning, high performance non-deep learning CUDA programming. But deep learning CUDA programming is actually the opposite, where we want to have low occupancy, or where we kind of need to do low occupancy. And in the recent cases, as we see, is actually single occupancy, and even actually less than one for Blackwell as well. So the idea is that for the same matrix size, if we, like we said, tensor core sizes are increasing, the MMA shapes are increasing. For the same matrix size, you actually have less working units. That means that we don't have that many working units for workers to assign to workers. And we kind of have to do that, assign one worker to one unit, one working unit in this case. So the reason behind low occupancy is actually related to NVIDIA's decision to strong scale the problem, strong scale the matrix multiplication problem. So strong scaling in this case refers to NVIDIA want to improve the performance across all matrix shapes, from small matrix shapes to large matrix shapes. The opposite case of strong scaling is weak scaling, where we use more tensor cores to run a larger matrix shape, and only guarantee a better performance on larger matrix shapes. Okay, so the third trend that we see is the increasingly asynchrony in execution, and the principle behind it, which is Amdahl's law. So as we saw, strong scaling, meaning that we want to improve the performance of the same matrix shape. Because of this, we kind of need to overlap workloads within like an MMA within an MMA operation. So here I show a diagram. Here the red and pink boxes are the data loading operations, and the green ones are the computation, the MMA operations. As we can see, tensor core size increase, tensor cores become faster, the time it takes to run MMA reduced. And as we further increase the performance of MMA, the data loading becomes a bottleneck. And we also know that another phenomenon is actually it's very hard to improve data loading performance, like achieving higher throughput. So the rate of improvement of memory loading can't keep up with the rate of improvement of tensor cores. So the way out of kind of like cheating Amdahl's law is by overlapping the execution, which is asynchronous execution. And so the graph, the table on the left is talking about every generation, NVIDIA introduces new features that are asynchronous, starting from Ampere having an asynchronous data copy, and then Hopper having asynchronous data copy, which is TMA, and then also having asynchronous in MMA. And Blackwell has even more fine-grained operations that are asynchronous, and its MMA and data loading are also asynchronous as well. Okay, so that's all I have for uh, the talk, and just like a small advertisement. I'm sure some of you have heard of SemiAnalysis, but probably a lot of you don't know what actually is SemiAnalysis doing. How do they make money, and do they actually survive on a very expensive newsletter? So yeah, SemiAnalysis is actually a research company that offers insights into the whole stack of the AI industry, starting from data center construction, um, from neo clouds, from all the way down to hardware and semiconductor manufacturing. And for my team, I'm on the I'll be more on the technical side of like research team. We create benchmarks and we create analyses and write um, blog posts like this Tensor Core evolution. And so this my focus is on ML systems and uh, can chat me on Twitter or everything. And this is the cover image that I really like for our article. It's created by Simon Guo. And a sneak peek of what we are doing recently, we're actually micro benchmarking B200s, and the graphs are related to the details of B200 of Blackwell, including another new feature called DSMEM. It's a distributed share memory, and then also a detailed benchmarking of TMA, its throughput, memory latency, and also the efficiency of different shapes of MMA on Blackwell. So if you're interested in this kind of work, um, feel free to DM me or send an email, shoot an email to letsgo@semianalysis.com and just put a title, put this ML hardware sys name on the title, and we should be able to see it. So yeah, thank you everyone for listening and happy to answer questions.
Questions. Prepare your questions, everyone. Whether it's about kind of just career stuff and what Kimbo does on a day-to-day, or if it's about the technical stuff. I have a bunch of technical questions, so.
Oh wow, okay. Should I brace myself?
Hi, thank you for the talk. It's really inspiring. You mentioned that the single semantics is kind of like a new revolution that's counterintuitive. Can you help us like develop the motivation behind it? Like, what's the trade-off there? In terms of like, what's the design trade-off there?
I think you're referring to the single occupancy thing. This one? Are you referring to this
I think it was before. There was a
before?
I think it's well architecture or one specific architecture introduced the single thread semantics, which is like only one thread can execute type of yes over there. The
The
last
Hopper,
one.
this one?
Yeah.
Yeah. So I think this is the idea of so a CUDA programming model is designed typically where a programmer actually codes in thinks in the execution of a thread. So you design a program where you do scalar operations, and then you utilize the hardware to massively parallelize and dispatch using hardware to run the same thing with a bunch of execution units. So the problem with this is that it doesn't really match well with a deep learning workload, or more narrowly speaking, the matrix multiplication. The main issue here is there are a couple of issues. One is the one that we refer to a lot, which is in the CUDA programming model, every thread is assigned to a set of register files, and only that thread can access those sets. But the problem is matrix multiplication actually requires a lot of registers to work. As we see, tensor cores are getting larger. You need more space. You need more memory to store the input and output matrices. But the threads, we don't. We would need more and more threads to store to gather a big enough memory pool. So the the problem with this, or I guess from the deep learning programmer's perspective, it's tedious to do something like this. And I guess it's probably like an internal conversation within NVIDIA, where they found that it's easier for kind of like changing the programming model, where instead of using a bunch of threads to launch to like gather a big pool of memory, or to run one execution MMA operation, you could just use one thread to perform this. Another benefit of doing this is that we talk a lot about asynchrony. So if we only if we only need one thread to launch a TMA loading, a data loading operation, that means that other threads are free to execute different workloads. They could be preparing for, could be calculating address generation, probably not Hopper, but they could be doing other workloads, maybe such as launching tensor cores, tensor core operations, launching MMA operations. So that's also like one motivation for doing single thread semantics. Does that make sense?
Yeah, that makes sense. Thank you.
Hi, my name is Yuan Fan, and I think in the talk you are seeing the two trends of tensor cores. The first one is the lowest occupancy, which means the higher scaling, and the other one is the asynchronous. So I think, do you think that more and more faster hardware development will cause a constant need of kernel optimization, like the kernel?
Is your question, do I think we would need more custom kernel development? Is that the
Yes.
question?
Yes, like flash attention.
Yeah, personally, I think throughout the history, the history of high performance computing, there is a forever tension between abstraction and performance. So more concretely, if you want to get the best performance, it's always beneficial to drop down to as low as you need to run to code low-level kernels. But abstractions help you develop things faster. So in my opinion, I think there will always be a need for developing custom kernels. But I think the recent development of AI, many startups are trying to automate this with AI, to write custom kernels with AI. And who knows, maybe someday AI could write it for us, and the custom kernel development would be a lot easier.
So sure.
Cole, go ahead.
Thanks. So I was also wondering, as you're going with this, the thread size is growing on these GPUs, as well as the async scheduling with the newer models. These seem kind of like CPU principles to me. In a way, do you see kind of like a paradigm change or merging between those two types of chips?
Mm, hmm. I would say it definitely feels, I think the asynchrony part, if you think of it as um, from a CPU architecture, it's kind of like you're doing like pipelining is a way of implementing asynchrony. So there is definitely some resemblance, I would say. Um, but I would say the trend of programming pattern is actually a data flow programming pattern. Um, so uh, for example, right now for a Blackwell GPU kernel, you would have one um, you would launch one thread or one CTA, and using one thread to launch one MMA, and another CTA would be or one CTA have multiple warps. One warp within one thread, within one warp, one thread would be launching an MMA. Let's say it will be launching a data loading operation. The data loading operation would be uh, synced up with an MMA operation with a barrier object. And then the barrier, after the barrier object is unlocked, the MMA operation would continue. So it's kind of more like a data flow. And this is actually very similar to the programming idea of systolic arrays. And uh, in some sense, like kind of like rock. So I would say it's more like a data flow pattern rather than a CPU programming pattern. But please don't quote me on saying that NVIDIAs are like rock. So
All right. Kimbo, I have a question. You said you're starting to look at distributed shared memory in your micro benchmarking. Any kind of
yes.
early results or insights you can share about it? Do you think it's a feature people will use? What will they use it for? Yeah, what's your opinion on distributed shared memory?
Yeah, so as far as I talking with the kernel writers, uh distributed shared memory is a feature that people use for kernel writers use for implementing where different SMs have intermediate results of the same tile, and then they perform like an all reduce. So that's like one pattern that they do. And I think for maybe mega kernel related workloads, one SM might reach for the like a synchronization lock or like a what's the word a semaphore that is inside the SMEM of another SM. So that's like I think another pattern. And so I think there is a usage of it. And so far we are seeing, we've already heard that DSMEM actually has a very low throughput compared to SM, which is like 128 bytes per clock. And so yeah, but we're still verifying like how bad it is actually. And this is like a preliminary graph that we have. I think hopefully we will get like more concrete numbers and more detailed analysis on this. Because another interesting thing about DSMEM is that actually DSMEM is related to GPC, which is the a cluster of SMs that are physically located clustered together on the GPU. And this is actually related to, this is actually can be different GPU by GPU. So it's very weird. Yeah, so hope that answers your question.
Yeah, it does. Any more questions from people? Yeah, one more. Yeah, go ahead.
You said that tensor cores have become more complex for ML practitioners. Is there abstractions currently, or is there like visions for certain like automation abstractions that for like ML practitioners to make it easy for them to like code and also like implement well? Like some sort of like maybe compiler optimization, I don't know, down the code level, to help assist like closing that gap.
Yeah, and maybe to add to that, just if you have any favorite abstractions right now, because I know there are a bunch, like what do you prefer to program in these days? So.
Oh man, there are like 30 DSLs and increasing. Yeah, I think that's a very good question and is a open problem. There are a ton of abstractions. I think the recent most successful one is Triton, which is sitting at a good spot for ML practitioners, but at the same time achieving a decent, like 90% performance of like the most the highest performing ones, which is Cutlass, I believe. And but the problem with Triton is ever since Blackwell, it kind of broke down. The abstractions don't work anymore. So people are the Triton team is lowering down to Gluon, which is basically from a Triton's perspective, breaking down one further abstraction below Triton. And it's got like a more complicated and so yeah, it's kind of a mess right now. And I would say right now on the lower level side, Triton is kind of breaking down, and right now people are working on Gluon. And then on the extreme performance side, Qt and Cutlass, in my opinion, is very difficult to understand. I still don't understand the layout and the thread value layout and everything. But for the people who understand, they find it very beautiful and their favorite abstraction. So that's one. And within NVIDIA, there's competing abstractions or competing programming frameworks, which is called Tile, GPU Tile IR, I think. Qtile, yes, Qtile. So that's like in the similar, around the similar place. So that's also one worth looking out for. And if we move upwards, there's Helion, which is supported by PyTorch. And it's even higher abstraction than Triton. I think it should be the most accessible one for ML practitioners. So yeah, I think to answer your question, I think there's no clear answer right now. And there's just a bunch of them, and probably need to take some time for everything to settle down and see what the industry or the world would cluster towards.
Thank you.
I have one more. I've heard rumors of like a hardware attention instruction coming from NVIDIA. I thought, who better to ask about rumors than SemiAnalysis person? So
I'm not the rumors guy, unfortunately. But I think the one that I know where Jensen says is attention operation or hardware, attention hardware is basically the exponential function, right? So they call it attention hardware operation, but in reality, it's accelerating the exponential function, which is very important to attention, to be honest, because according to Tree Dao, who wrote the Flash Attention 4, the bottleneck, the exponential part of the softmax inside the attention operator is becoming a bottleneck. And I think the B300s accelerated the softmax, not softmax, the exponential operator or the exponential hardware unit by, I think, 2 times or something, at least by a decent amount, and removing the bottleneck. And these are all confirmed and open information. So yeah.
Makes sense. Maybe a final question from me is any comments on other hardware like TPUs and how now that they're being sold, through Broadcom and like will they take over? Like, do you think people need to continue kind of struggling through the software abstractions to be able to program GPUs? Will we get a GPU with Tensor Core only and it will be super simple and we don't have to think about, threads and SMs and all of that? And maybe also just to add to the question, Grok acquisition and all of that, like how does it all play? Like maybe 5 years, 10 years from now, what do you think will AI hardware will look like? So
Mm. So first of all, I would say this is a type of question that probably Dylan should answer. He probably has a better idea of the overall industry. So my opinion would not represent SemiAnalysis. Um, in my opinion, I think NVIDIA still has a very strong hold um, the in the industry. So the major moat, you would say, is still probably around um, the flexibility of programming. It's hard to program, but it's flexible enough to explore adjacent uh, machine learning model ideas. Whereas TPUs are designed very strictly just for accelerating matrix multiplication. And it actually referring to the, someone just asked the CPU programming model. TPUs actually work like CPUs more. They don't process matmuls um, asynchronously. They actually do in a single thread fashion. Um, so they have a totally different programming model, and they work very well for Google. Google has a ton of um, super cracked engineers who find programming it very easy. Um, so I think it'll continue like that for them. But for academics, for people outside of Google, for people who don't have the best Google engineering team for help, I think CUDA will still be here for stay for some time. And as for Grok, honestly, um, I actually don't understand either. Um, like among all the accelerators, I don't understand why they would want Grok. Um, so I don't know. Yeah, I don't really know what to say about that. I personally think the idea is interesting, but they suffer the same issues with all the other accelerators. Um, so yeah. So to summarize, I think CUDA is still here to stay, and TPUs would still probably do very well. But I think the major academics and engineers would still probably be using NVIDIA GPUs for some time.
So, okay, if there are no more questions, thank you so much, Kimbo, for coming. This was great. I loved the talk.
Okay, thank you, Mohammed. Thank you, everyone.
Hopefully, we'll catch up when you're back in New York. So,
Oh yeah, definitely.
see ya.
Okay, see you. Bye, everyone.